Hello everyone, welcome to the channel Statistic Hub. So in the previous lecture, we have studied the concept of linear transformation. Okay, let's continue it further. So we study the linear transformations over the vector spaces and over matrices. This is what the linear algebra is all about. Okay, so like rotations, reflections, um, projections, similarly differentiations, integrations, the transformations of all these. Okay, so in linear transformation, we have studied in the previous lecture that we have two vector spaces over the field f. Okay, and the mapping, which is t b to w, is said to be the linear transformation if t of alpha plus beta equals to t of alpha plus t of beta for all alpha plus alpha comma beta belongs to the vector space V. And the second condition is that T of C alpha equals to Ct of alpha, where C belongs to the field and alpha belongs to the vector space V. Okay, and if we put C equals to 0, it gives us Ct of 0 equals to 0 in second equation. Okay, and it means that every linear mapping takes the 0 vector into 0 vector. Okay, that's what that means. Okay, so now let's see, and I have also defined the matrix mapping. What? Matrix is as the linear transformation as that I have the matrix of A m cross n and the mapping is from r's power n to r's power m. Then this mapping, this transformation is defined as AU, where A is of m cross n and u is of n cross 1, then the resultant of this would be m cross 1, which belongs to r's power n from this. Okay, so this is the matrices as linear transformation. That's how we can define this. Okay, now let's see the examples of the when the projections and the rotations or happens, how these happens in the linear transformations. Okay, so let's see rotations in plane first. What? Rotations in planes. Okay, how can the transformation be performed here? Okay, so if I have the transformation, if I have the mapping as t r square to r square, and I have the matrix as cos theta minus sin theta and sin theta, and this is our cos theta. Okay, now it has the property that it rotates every vector in r square. Okay, counterclockwise about origin, though the angle theta. Okay, that's what we are saying. We are saying that it has the property property that it rotates it rotates every vector in r square counterclockwise counterclockwise about origin throughout the angle theta. Okay, now I want to check this statement whether it is true or not by this transformation. Okay, so let's see it like this, that I have said this is my x-axis and this is my y-axis. Okay, and it has a property that it rotates every angle, every vector in r square. That there is a vector, let's say b, in which belongs to the r square. Okay, and the b vector is defined as x comma y. Okay, this is my vector. Let's say this vector is here. Okay, x comma y. Then it rotates every vector in v square in counterclockwise about origin with the angle theta. I want to prove this by the if the transformation goes like this. Okay, this is my corresponding matrix. Okay, now what is this vector v equals to x comma y? I can draw this vector as like this. Okay, this is my vector v. Okay, now this vector v, where the point x lies here, this is the distance x. Okay, and this is the point y is here, so this is the distance y. Okay, and if this vector v makes the angle, let's say alpha, with the x-axis. Okay, alpha is the angle made between x-axis and the vector v, okay, and the line vector and the line, let's say give it name OC. This is my line OC of the vector v. Okay, now I want to find x and v corresponding to this alpha. So if I apply cos alpha, which is equals to base upon hypotenuse, base upon hypotenuse, what is the base here? Base here is x. Okay, the length here is x, x upon what is the hypotenuse? Let's say this is our r. Okay, the hypotenuse is r, x upon r. Then from this I got that x equals to r cos alpha. Okay, similarly if I want to find y, then this is my y. Let's draw it like this. Okay, then if I apply sine alpha, the angle sine alpha, it would give me perpendicular upon hypotenuse. Okay, and what is my perpendicular? Here the perpendicular is the distance y, which is equals to y upon r. So from this I got that y equals to r sine alpha, r sine alpha. So my v vector is actually r cos alpha and r sine alpha. Okay, and by applying Pythagoras, what is my r? R is root of x square plus y square. Okay, now we'll apply the matrices as linear transformation. We have studied that, and that is that P of v vector equals to a v. That's what we do in the matrices linear transformation. This is my corresponding transformation. Okay, we'll apply this. My A matrix here is cos theta minus sine theta. Okay, sine theta cos theta. I am transforming this vector v, which belongs to this r square vector space v, okay, to the uh, to r square, and I want to find when it moves to the counterclockwise, what will be the angle, what will be the corresponding vector that it makes. Okay, and we are transforming this, and what is the vector v? It is xy, xy, and what is the value of xy? It is r cos alpha and r sine alpha. Okay, now we will just multiply them. It will be r cos theta cos alpha minus r sine theta sine alpha, and this would be r sine theta cos alpha plus r cos theta sine alpha. Okay, and we'll if apply the trigonometric rule here by taking r common in the first one, it would be like cos theta plus alpha. This is the trigonometric formula for cos of a plus b, which is cos a cos b minus cos sin a sin b. Okay, similarly for this one, if I take r common here, then it would be sin a plus b, because sin a plus b equals to sin a cos b plus sin a plus cos a sin b. Okay, so it would be sin of theta plus alpha. Okay, so this is the linear mapping here of the vector v. Okay, so if we look at here that my corresponding new angle theta plus alpha is my new angle here. Okay, this is the angle between x-axis and the clockwise, counterclockwise to the transformation, the linear mapping. Okay, so it would be like this: theta plus alpha. This is alpha and this is theta. Okay, and it is moving counterclockwise. You can see that it is moving counterclockwise because it is making this whole angle is alpha plus theta. Okay, and this is our new vector, which is r cos. This remains same, the length of this vector would remain same, and it is moving counterclockwise, and then under new vectors are r cos theta plus alpha and r sin theta plus alpha, r plus sin theta plus alpha. Okay, so the transformation of the new vector of the vector v, which belongs to r square, Okay, and I have transformed this vector to R square, where the corresponding statement is this, the corresponding matrix is this. Okay, and I got by transforming the new vector as like this. And the resultant of this, like this point is my t of x comma y, the mapping, and it goes like this. This is my uh, direction, counterclockwise direction. It is moving like this. Okay, and we can see that the distance r is remaining same. Okay, in this it is same, and this vector v, it is also r, and this it is also r. Okay, so here theta plus alpha is the angle this, and TV, T of V, that's what we have find here, is a vector results from the rotating vector V in the counterclockwise direction. Okay, that I have got this vector TV after rotating the vector V in the counterclockwise direction, then the angle would be from alpha goes to alpha plus theta, and the vectors, the corresponding coordinates of the vector changes to this. Okay, this is the transformation, or you can say the linear mapping of the rotations when we rotate a plane. Okay, that's how we can find this. And similarly, if we look this projection in the projection, then let's say the mapping is from r cube to r cube, and take the matrix as, let's take it 1 0 0 0 1 0 0 0 1. Okay, now there is a vector v which is equals to x y z, and I want to see the projection of this vector. Okay, let's find this av matrix mapping. We are applying the matrix transformation here. Okay, then av equals to 1 0 0 0 1 0 0 0 0, and if v, what is v is x y z, then I got the t of v, which is equals to xy0, which is xy0. You can see it like this, that let's say this is x, y, and this is z. Okay, and I can't really show it in the three dimension, but let's just assume this is our vector v, which is x, y, z. Okay, now the projection of this vector, we are finding the projection of this vector is the resultant as xy0, which is in the xy plane. This is our xy plane. Okay, now the projection of this vector goes like this. Okay, it is somewhere like xy0. You can see that this is a projection of xyz. Okay, so that's how we can use the topic linear transformation in the rotation, reflection, okay, projection, similarly differentiation, and integration, whatever this is. There are many uses of this linear transformation. It is very important in our further studies, whether you study economics, statistics. This topic or this linear algebra is very helpful in that case. Okay, now there is an important topic in linear transformations that is said as kernel of t, or you can say null space of t. Null space of t. Okay, let's see this. So my linear mapping here is defined as t v to u. This is a linear mapping. Okay. Then the kernel of t, or you can say the null space of t, is the set of all those elements in V. Set of all those elements in V. These are the corresponding elements in V, which maps to the zero vector. This is our zero vector. Set of all those elements in V, which maps to the zero vector in U. Okay, now I can write it as like this, that ker of t is defined as set of all those elements in V which maps to the zero vector. That's how we can define it. Okay, now if I say that my mapping, the corresponding mapping is injective. If my mapping is injective, then I got that t0 equals to 0 is the only pre-image that I have. Okay, is the only pre-image that I have. Okay, and in that case, my char t would be equals to 0. How? Because if t is injective, if t is 1 1, Okay, then this is v, this is u. Okay, if t is 1 1, and we know in the linear mapping that every zero vector maps to the zero vector, every zero vector. Okay, for every linear mapping, and we know that it is a linear mapping, and we are taking it as an injective. So zero vector will map to zero vector, will map to zero vector, as it is 1 1. So no other vector can map to the zero vector again. Okay, so this is the only pre-image that we have, t0 equals to 0. So from this we got that char t equals to 0 if and only if uh, t is injective. Okay, what do we say that? That if I have the transformation tv to u is a linear mapping, then t is injective. This transformation is injective, you can say, if and only if my char t is equals to 0. Okay, okay. Now, what is the image of linear mapping? Let's see that. The image of linear mapping, or you can say the range of t. Okay, range of transformation t. So if I have the mapping as tv to u, then image of t is defined as like this. Let's say this is my vector space v. Okay, and this is the domain of this vector space. Okay, this is the domain. This area is the domain of the vector space. Domain of vector space. And this is the kernel of T. What? Kernel of T. Or you can say the all those elements which maps to the zero vector. Okay. And this is my another vector space which is W. It is W. W. And this is the range of W. Or this is the range of W. And this mapping is goes like this, and this is my zero vector. So all the kernels of T are mapping to the zero vector. This is our mapping. Okay. Then we say this is our char T. Okay. Now this whole is the range of T. This whole is the range of T defined as defined as u belongs to u. All those vector in u, or you can say, sorry, here we have w. All those vectors, all those u vectors in the w, if there exist v belongs to v, for which t of transformation v equals to u. Okay, yes, you got it. Like all those mappings, let's say this is my v, this is w, and we are mapping it like this. The transformation goes like this. Then all those elements, all those vectors in this w vector space is the image of the transformation. The transformation is defined as like this. Okay, now these are our image of t. Okay, now I have another thing which is as that transformation is v to u is a linear mapping. Now there are two things, that char t. Char t is a subspace subspace of vector space v, and other thing is as that image of t forms a subspace of w. Let's see it how. I have said that the transformation is v to u, sorry, u, that the transformation is v to u, then the kernel of t forms the subspace of v. It forms the subspace of v, and the image of t is a subspace of u. Let's see it. So for the subspace, there are three things which are as that the zero vector belongs to that vector, belongs to v. Okay, as it is forming subspace, that zero vector should also zero vector belongs to char t, is it is forming subspace. That if there are two vectors which belongs to char t, then the sum of these two vector also belongs to char t, that u plus v belongs to char t. And similarly the third one is that cu also belongs to char t, the multiplication one. Okay, so these are the conditions for vector to be a subspace. Okay, for a set to be subspace. So let's check it here as t0 equals to 0. This is that we have in the linear mapping. Okay, now if I let two vectors u comma v which belongs to the char t, okay, then transformations of this u plus v is defined as tu plus tv, and as these are belonging to the char t, then the corresponding mappings of these would be 0 and it is also 0. So this is equals to 0, and which belongs to, as u comma belongs to v belongs to char t. So from this we got that u plus v, as it is also mapping to 0, u plus v also belongs to char t. Okay, now let's check for t of cu, where c belongs to the field. It will be c of t0, and t0, as it is belong to char t, it will be 0. Okay, so from this we got that u belongs to char t, and there is a c which belongs to the field. Then t of cu, which is also mapping to 0, it also belongs to char t. So from this we got that char t is a subspace of V, as it is satisfying all the three properties for the subspace. Okay, similarly we'll see for the images of T that all the images or ranges of the transformation is a subspace of U. Is a subspace of U. Let's see it like this, that T of 0 equals to 0. It is the required condition in the, it is the required condition in the all the linear mappings. Okay, so it exists in all those. Okay, now let's consider two mappings, which is T of U, T of V are vectors in image of T. Okay, this is like this, v u, these are the corresponding vectors in u now. So it will be t, let's consider t of u, t of v are vectors in image of u. Okay, now t of u, the sum of these two, t of u plus t of v would be written as t of u plus v, which also belongs to this range set t. This is the corresponding range set. Okay, and similarly that ct of v can be written as T of CV, which also belongs to the range of T. Okay, so from this we got that T of U belongs to the image of T, T of V belongs to the image of T, then the sum of these also belongs to the range of T, and the multiplication of this also belongs to the range of T. So it also forms a subspace of U. Okay. Okay. Now when I say when I say that is a set of vectors v1, v2 to vn, okay, which is spanning a vector space v. Okay, this is a set of vectors which is spanning a vector space v. Okay, and there is a mapping which is as t v to u, and this is a linear mapping. Okay, now what are the corresponding images of this? The corresponding images of these vectors are t v1, T V2 to T Vm. Okay, the map by the mapping this is the mapping which spans the image of T. This is the result. There is a result which is as that if I have a vector space v1 to vm which is spanning my whole vector space, then if there is exist a mapping which is v to u and it is linear, then the corresponding tv1 transformation, then the corresponding mapping which is tv1 tv2 to tvm spans the image of t. Let's see it how. So if I have a vector, let's say u, which belongs to the image of t. Okay, and this means that there exists a vector v for which that it is a pre-image. Okay, so there is exists a vector v which belongs to the vector space v. Okay, for that it is the image set. Okay, such that that t of v equals to u. Okay, now because VIs are the set of vectors which spans the whole vector space, and if there exists a V vector which is belonging to this vector space V, then this vector V can be written in their linear combination, in the linear combinations of the VIs vector. For the scalars, let's say AIs. For the AI scalars, it can be written as A1 V1 plus A2 V2 to am vm, as it is spanning the whole vector space. Okay, now what is my u? U is the t of v. Okay, u is my t of v. So I can write u equals to t of v, which is equals to t of this whole, which is a1 v1 to am vm, which can be written as a1 t of v1, as t is linear. I can write it as like this, am t of vm. Okay, so from this I got that I have taken u as the vector in image of set, and you can see that every vector in the image set can be written in the linear combination of t of v1, t of v2 to t of vm. I have written it like this. Okay, so from this I got the result that t of v1, t of v2 to t of vm are spans the image of t, as it is written in their linear combination. Okay, now this is a very important result actually. Okay, it is a very important result because it is used in very uh, examples or in solving questions. So the result is as that v1 to vm spans a vector space v, and suppose that tv to u is linear, that the transformation is linear, then t of v1 to t of vm spans the image of t. Okay, now there are some theorems which are as that if my mapping is tv to u be a linear mapping, be a linear mapping. Okay, and if char t is equals to 0, char t equals to 0, then image of a linearly independent set of vectors in V are linearly independent in U. Okay, and this set of vectors be alpha 1 to alpha n. Okay, so what is saying? It is saying that let this is the transformation which is a linear transformation, and char t equals to 0. Char t equals to 0, it means the mapping is injective. Okay, then image of a linearly independent set of vectors, image of a linearly independent set of vectors, these are some vectors alpha 1 alpha 2 to alpha n in v, which are linearly independent, then the image of these vectors in u, image of these vectors in u are linearly independent. Okay, so we can see it like this, that for linearly independent, we have to check the linear independence of this. That is t of alpha 1 to t of alpha n. These are the corresponding images of the alpha 1, alpha 2 to alpha n linearly independent sets. Okay, now we have to check the linear independence of this image set. Okay, so for checking the linear independence of this, okay, we can write it as c1 t of alpha 1 plus for the scalars. Okay, c1 t of alpha n equals to 0. Okay, so for linear independency, our constants, which is c1 c2 to cn, has to be all ci's are equals to 0. Okay, so for calculating this, we can substitute it as t of c1 alpha 1 plus cn alpha n, which is equals to 0, by the property of linear transformation. We have studied this in the previous lecture, and we can see that because t is linear, I can write it as this. Okay, like this. Okay, now because t is linear, we have very important result, which is there is an important result, which is t0 equals to 0. Okay, that every vector in 0 maps to the 0 vector. So this result has to be satisfied because t is a linear mapping. So t0 equals to 0 is the required result here. So c1 alpha 1 plus cn alpha n has to be equal to 0, and for this whole equation has to be 0, there is only one solution of this, which is that for this whole to be 0, all the ci's has to be 0, c1 c2 to cn. R has to be equals to 0, because we know that alpha i's are independent. Our alpha i's are independent. This is given in the equation. This is given in the theorem. Okay. So as all the alpha i's are independent, all the constants of these, which is C1, C2 to Cn, has to be equals to 0. Okay. Now we got that all the Ci's are equals to 0. So from this we can say that all the T alpha 1, T alpha 2 to T alpha n are linearly independent. Okay. So the corresponding result is like this, that if I have a mapping which is linear and the kernel of T is equals to 0, okay, and the kernel of T of that mapping is 0, then the linearly independent set of vectors in V, these are the corresponding linearly independent sectors in V, and the images of these vectors are also linearly independent in U. Okay, now let's see the second theorem, which is as if there is a mapping TV to U and that mapping is linear. This is a linear mapping, and the vectors which are alpha 1, alpha 2 to alpha n, which is there is a set of vectors, and this set of vector is the basis of V. Okay, this is the basis of V. Then vectors T alpha 1, T alpha 2 to T alpha n generate generate image of T. Okay, what is it saying? That if this is a mapping, okay, T V to U, and these are the corresponding basis vectors of the vector space V, then the corresponding mapping of these vectors T alpha 1, T alpha 2 to T alpha n, it will generate the image of T. We can see it as like this, that if there is a vector E which belongs to the image set of T, okay, image set of T, this is our corresponding image set U, this is our image set. Okay, now then for this image vector, there exists a vector, let's say alpha in V as such that T of V equals to E. Okay, then only this vector E will exist if there is a transformation, something like that. Okay, now as alpha is a vector in V and the corresponding basis of this vector space V are alpha 1 to alpha n, so I can write this alpha in the linear combinations of these basis vectors. That's what basis vector is all about. Okay, so alpha equals to, for the Ci's as scalars, C1 alpha 1 plus C2 alpha 2 to Cn alpha n. Okay, now by taking the transformation, which is T of alpha, T of alpha equals to T of C1 alpha 1 to Cn alpha n. Okay, and what is my T of V? T of V, sorry, it is V. This is V. Okay, T of V is equals to E. Okay, is equals to E. So it maps to the E vector in U. Okay, and I can write it as C1 T of alpha 1 plus C2 T Cn T of alpha n. Since T is linear, I can write it as like this. Now from here you can see that T of alpha I belongs to the image of T, and it follows that every image vector, you can see that every image of T is generated by, every image vector is generated by T of alpha 1, T of alpha 2 to T of alpha n. This is, we are taking every image vector, every image vector. So every image vector E which belongs to the image of T is generated by T of alpha 1, alpha 2 to alpha n. Okay, I think you got it. Okay. Now from this we gain a note. There is an important, very important note, that my mapping is from TV to U, and I have the vectors alpha 1, alpha 2 to alpha n as my basis of vector space V, and then I have T alpha 1, alpha 2 to T alpha n is the spanning set of U. Okay, that's what we have done here. Okay, now further, if I consider that my T is injective, if my T is injective, okay, that means my cat T is equals to 0, cat T equals to 0. Then if my cat T is equals to 0, then it means that the corresponding spanning set, which is T alpha 1, T alpha 2 to T alpha n, is the basis for U. Okay, is the basis for U. If T is injective, that means ket is equals to 0, then the spanning set here would be linearly independent. Okay, as ket is equals to 0, then if this would be linearly independent and it is also spanning set of U, then this would generate the basis of U. Okay, okay. Let's see an example which is as if my transformation is from r cube to r cube and the transformation is defined as x1, x2, x3 which is equals to x1 plus x2 plus x3 and 2x1 plus x2 plus 2x3 and x1 plus 2x2 plus x3. Okay, and where x1, x2, x3 belongs to r cube. Okay, now I want to find here ket. uh, is it 1 1? I want to check whether it is 1 1 or not. 1 1 and image of t. Okay, I want to find all these things, these three things. So for ket, we can write ket as all those vectors in r cube in the vector space, this one r cube, that maps to the 0 vector tx equals to 0, tx equals to 0, which means that t of x1 x2 to x3, all those vector which maps to 0. So I can write it as x1 plus x2 plus x3 equals to 0, 2x1 plus x2 plus x3 equals to 0. Similarly, x1 plus 2x2 plus x3 equals to 0. Okay, now let's just simplify these three equations as I can substitute here and it's just negative, 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 and it could give me x1 minus x3 equals to 0. x1 minus x3 equals to 0. Sorry, it is, yeah, x1 plus x2 plus x3. Okay, uh, okay, it is 2x3. I'm getting it wrong. So x1 plus x3 equals to 0. Similarly, if I put this equation here, it would give me x1 plus x2 plus x3 equals to 0. And this will be x2 equals to 0. So we got that x1 equals to x2 equals to x3. I can write it as like this, which is 1, 0, minus 1, and let's denote it as a constant k. Okay, so I got x1, x2, x3 as k of 1, 0, minus 1, where k belongs to r. Okay, so my char t is equals to k of 1, 0, minus 1, and where k belongs to r. And if I look at the dimension of this char t, the number of vectors in char t, which is as 1. Okay, we'll look to the dimension concept in the next lecture. Okay, so you can also see that for 1 1, my function that char t, that t is 1 1 if only char t is equals to 0, but here char t is not equals to 0, it is of dimension 1. Okay, so the transformation t is not 1 1. Okay, now I have to find the image of t. For finding the image of t, let's see it here only. I have t of x equals to like this. Now I can write it as x1 1 2 1 as in the form of vectors 1 2 1 plus x2 1 1 2. Similarly for x3, which are as 1 2 1. Okay, so from this, I got that the corresponding Tx, it is a linear combination of 1 to 1 and 1 1 2 vectors. Okay, here these two vectors are same, 1 to 1 and 1 to 1. Okay, so Tx is a linear combination of 1 to 1 and 1 1 2 vectors. So I got that image of T is generated by L1 1 to 1 plus L2 1 1 2. Okay, so these are my image vectors, and the dimension of these image vectors are 2. as there are two vectors in this. Okay, now we can also find the image vectors as by using the standard basis. Okay, like if I have the standard basis, we have the vector space RQ. So the standard basis of this will be E1, E2, E3, E1, E2, E3. There will be the corresponding standard basis for RQ. Okay, and alpha 1, alpha 2 to alpha 3 is the basis of RQ, the original basis. Okay, and the image of T is the linear span of T alpha 1, T alpha 2 to T alpha 3. That's what we have studied in the previous two theorems. Okay, we have studied in the earlier theorem this. Okay, so I can write it as that T of E1 equals to 1, 2, 1. The vectors which we have generated here, which is 1 to 1 and 1, 1, 2. Okay, so T of E1 equals to 1 to 1. T of E2 equals to 1, 1, 2. It is mapping to this. And T of E3 equals to 1, 2, 1. Okay, these are the corresponding three vectors which we have got earlier. Okay, now these TE1, TE2, TE3 are the spanning set of image of T. These are the spanning set of image of T. And you can see that T of E1 and T of E3 are similar. Okay, so the linear span of image of T, the image of T is a linear span of TE1, which is 1 to 1 and 1, 1, 2. So the image of T would be L of 1, 2, 1 and 1, 1, 2. So here we are just using the standard basis to find our image vectors. We can also do it previously where we didn't have taken the standard basis into account. Okay, okay. Uh, Now, as I have taken into the account of the concept of dimension of charity and dimension of image of T, image of T, that are said to be, these are actually said to be the dimension of charity is said to be the rank of T, sorry, nullity of T. Nullity, I'm sorry. It is said to be the nullity of the transformation, and dimension of image of T is said to be the rank of T. Okay, so we will study this concept earlier, sorry, in the next lecture in more detail. Okay, so that's it for now. Thank you.